Hi everyone, this is a presentation of Proxy Synthesis, learning with synthetic classes for geometric learning. I'm Byungsoo Ko from Naver and Line Corporation. Let's get started by introduction. In image classification task, we classify an input image according to shared figure semantics, where the class information are the same between training and test data. In comparison, the purpose of metric learning is to learn a similarity function that measures how similar objects are. One major difference is that the class information between training and test data are different. So metric learning may require higher level of generalization than classification task. In metric learning, there are two lines of loss functions, pair-based and proxy-based losses. In pair-based loss, it considers the relation between embeddings, and it tries to pull samples from the same class and push samples from the different class. And because of its large amount of possible pairs, it suffers from training complexity and sampling issues. To alleviate this issue, proxy-based loss has been proposed by introducing proxy feature, which is a class representative feature. In proxy-based loss, it pulls the anchor embedding and positive proxy and push the anchor embedding and all other negative proxies. In this work, we include softmax variants such as softmax, arcphase, and cosphase into proxy-based losses because a proxy has the same meaning with the class weight in softmax variant. Our motivation is that when there is a distribution shift between training and test classes, most of the metric learning functions try to fit well to the training data, and this can cause overfitting to seen classes and leading to lack of generalization on unseen classes. So we propose a novel regularizer for proxy-based losses called Proxy Synthesis. It generates synthetic embeddings and proxies which work as synthetic classes and train the model including them. Training with synthetic classes improves generalization performance by considering class relations and obtaining smooth decision boundaries. I'm going to explain the details in the proposed method section. And for the advantages of proxy synthesis, it is simple because it only requires linear interpolation to generate synthetic classes. It is flexible because it can be used for any softmax variant and proxy-based losses. Also, it is powerful because it outperforms over existing methods for a variety of losses in image retrieval tasks. In this section, we introduce related works and compare them with proxy synthesis. For better generalization in metric learning, previous works generate synthetic samples to increase the number of instances or obtain more informative samples. However, previous works are proposed for pair-based losses, which can still suffer from the training complexity and sampling issues, when proxy synthesis is proposed for proxy-based losses, which can alleviate those issues. In previous works, the generated synthetic samples only work for seen classes from the training data, when proxy synthesis used the synthetic embeddings and proxies as synthetic classes for generalization to unseen classes explicitly. Proxy synthesis shares the similar concept with mix-up techniques in terms of interpolating features for augmentation. However, there are major differences. Mix-up techniques are proposed for generalization to seen classes in classification task, while proxy synthesis is proposed for generalization to unseen classes in metric learning task. Mix-up techniques interpolate input images or hidden representation and one-hot labels to use them, such as 70% of cat and 30% of dog. However, proxy synthesis interpolates embedding and proxy features in output space, which does not require additional forward propagation, and use them as new synthetic classes. Because of this property, proxy synthesis shows better generalization in metric learning task, and we are going to discuss about this more in the experiment section. There is a related work which uses virtual class in classification task. It is called virtual softmax, and it generates virtual class weight to increase the interclass variation. However, this method generates a single class weight, and it is only applicable to softmax. In proxy synthesis, we generate multiple synthetic classes, including synthetic embeddings and proxies, and it is applicable to every softmax variant and proxy-based losses. From this section, we are going to introduce the details of proxy synthesis. This is how proxy synthesis works. In the first step, we process input data with the network to obtain embeddings and proxies, and then we generate the synthetic embedding and proxy by linear interpolation, and the linear interpolation is done by I function when the lambda is randomly sampled from the beta distribution with alpha hyperparameter. And the number of synthetic pair is decided by mu hyperparameter. For example, if the mu is 0.5, then we generate synthetic pairs of half batch size. Finally, we compute a proxy-based loss, including the synthetic classes. Then you may wonder why the proxy synthesis works. First reason is proxy synthesis considers class relation during training. We want to get a well-structured embedding space, and it should contain meaningful relations among embeddings. For example, there is a research that king minus man plus woman embeddings are similar to queen embedding in a word embedding space when the model did not train with this relationship. To achieve this kind of property, we explicitly insert in-between class relation with synthetic classes. For example, by mixing wolf and dog, we create wolf-dog classes as synthetic class. Then these synthetic classes will mimic unseen class during training phase. So this in-between class relation is considered in both forward and backward propagation. In proxy-based loss, it considers embedding and its corresponding proxy relation in forward and backward propagation. In comparison, proxy synthesis considers in-between class relation with synthetic class, which is x tilde and p tilde, in both forward and backward propagation. The second reason is that proxy synthesis allows a model to obtain smooth decision boundary. The smoothness of decision boundary is a main factor of generalization. So we perform an experiment with isotropic Gaussian dataset, including red, gray, and blue classes. We train the model with blue and red classes when the gray class is remained unseen. The darker the intensity of blue or red in the background, the higher the prediction confidence to corresponding class. We can see that norm softmax loss shows strict decision boundary, while proxy synthesis shows smooth decision boundary for both input and embedding space. The strict decision boundary is constructed when the network always outputs embedding feature close to the corresponding proxy, even though the input has shared feature semantics among different classes. And this is more critical to metric learning because the embeddings would not represent feature semantics properly for unseen classes. This phenomenon can be proved theoretically. We compare the gradient descent of softmax loss and proxy synthesis combined softmax loss. The gradient of loss over x can be derived by this equation, and the tau I is always negative and tau k is always positive. And this means that the embedding x always try to be close to the corresponding proxy pi and distant from negative proxy pk. Because of this, the strict decision boundary is constructed. On the other hand, when we use the proxy synthesis, the gradient for synthetic classes x tilde and p tilde can be derived by this equation. And the tau I prime is positive and tau j prime is negative. And this means that the embedding x try to be distant from the corresponding proxy pi and close to negative proxy Pj. And this will regularize the previous softmax loss situation and obtain smooth system boundary with better generalization. In this section, we are going to discuss about experiments. We visualize embedding space with TSNE visualization. In figure A, train embedding is gray dot, and test embedding is pink dot. We want to make a model that is robust to unseen classes of pink dot by training with seen classes of gray dot. In figure B, synthetic embedding is green dot, and we train a model with these synthetic classes to mimic the unseen classes of pink dot. Then these additional training signals enable the model to capture extra discriminated features for better generalization. In the impact of synthetic embedding and proxy experiment, we perform ablation study by differentiating embeddings and proxies. We observe that even though we use only synthetic embeddings and proxies in model 2, it shows decent performance with small degradation compared to the baseline. Model 3 and 4 show that using synthetic embeddings and proxies with original embeddings and proxies give performance boost compared to the baseline. And finally, using all the original and synthetic embeddings and proxies achieve the best performance. Proxy synthesis generates synthetic classes by random sampling from beta distribution. In the impact of hardness experiment, we compare static and stochastic generation for synthetic classes. The experimental results show that the stochastic generation is better than the static generation because it can generate the greater number of variation. Moreover, it shows that instead of generating too close to original class, such as lambda 0.1 or alpha 0.2, enough hard synthetic class shows better performance such as lambda 0.2 and alpha 0.4. We visualize logit to compare prediction confidence in logit visualization. In the heat map, the x-axis is proxy and y-axis is embedding, while the diagonal is ground truth logit. Num-softmax loss shows high confidence prediction with red diagonal. In contrast, the proxy synthesis has lower confidence prediction in D1 and D4 with yellow diagonal. This is because of the hard competitors in D2 and D3. This will allow the model to obtain smooth system boundary. To see the robustness to input and embedding deformations, we perform following experiments. In the input deformation, proxy synthesis improves performance to all kinds of input deformation by minimum 1.3 and maximum 2.5%. In embedding deformation experiment, we generate synthetic embeddings by linear interpolation with lambda for both query and gallery set. Then synthetic embeddings in query set are used to find the other synthetic embeddings generated with the same manner in the gallery set. The experimental results show that proxy synthesis improves performance on both train and test embedding deformation by about 20%. And we compare the proposed method with other regularizers, including virtual softmax, input, and manifold mixup. In image retrieval task, proxy synthesis achieved the best performance, and in classification task, manifold mixup achieved the best performance. And this result shows that proxy synthesis is more suitable for improving generalization on unseen classes because of exploiting synthetic classes. This is the comparison with state-of-the-art. We evaluate our method with two evaluation procedures, conventional and MLRC evaluation. MLRC evaluation is recently proposed in ECCV 2020 and present fair evaluation protocol for metric learning, which includes hyperparameter search, four-fold cross-validation, ensemble evaluation, usage of fair metrics. The experimental results show that proxy synthesis improves performance of softmax variant and pair-based losses in every benchmark dataset. Also, the improvement is shown in every metric for both conventional and MLRC evaluation. This is it, and thank you for your interest in our work.